Welcome back to the lecture series on topology and metric spaces. So far we have discussed regarding topologies like product topology, compactness properties and all. Also we have discussed the Heine-Borel theorem and also the special compactness properties in case of metrizable topological spaces. Now let's go ahead. So today we are going to start with something called separation property. It's also very important to study the geometric of another spaces where topology is induced. So before start with, let us see some definitions. So first is that something called T1 space. So what is a T1 space? Let us consider that. So let us mention that X is a topological space. So X is said to be T1 space if, and let's say if, for each small x belongs to capital X, we have singleton X is closed. Means every singleton points are closed. So for example, any finite discrete topology next is something called T2 space. So T2 space means, or we can consider, let's say, some more, let's say R with normal Euclidean topology. Like if we consider here's my real line, here's my small r, then capital R minus singleton r is basically nothing but minus infinity to r union with r comma infinity. So this is an open set, this is an open subset. So the entire union is open subset. Okay, so that means this is open, so that means small r is open, basically small r is closed. Okay, next is something called T2 space. So T2 space means let small x1 and small x2, this belongs to capital X, then there exists ux1 which contains small x1 and ux2 which contains small x2, such that ux1 intersection with ux2 is empty, means both the open neighbors are disjoint and both ux1 and ux2 has to be non-empty. That need not give any more motivation here, because we have already considered that x1 is in ux1 and x2 is in ux2. Okay, and of course we should make it here that x1 is not x2. So any two distinct points can be separated with disjoint open neighborhoods. Okay, so remember that in case of this, in case of T1 space, okay, we'll define it. Okay, we'll give overview later, but let us first list the definitions. Next is something called T3 space. So as an example, Rn with Euclidean topology. Okay, or we can consider any discrete topology. Alright, so T3 space means let x belongs to capital X is a point and V subset of capital is a closed subset, is a non-empty closed subset. Okay, so if we consider that x1 any particular singleton point and any non-empty closed subset that does not contain this point that I have chosen, then this singleton point and this closed subset can be separated with disjoint open subset. So that means there is certain ux1 is subset of x and is open subset. There is open subset ux1 and open subset uv such that x1 is in ux1 and v is inside uv. Okay, so can you give me an example here? So as an example, let's say R with normal infinite topology, it's T3 space. Okay, so it's quite easy. Like if we consider that let's say small x here and any closed set like this, let's for example you consider any closed interval a comma b, then we can take any open set. So what I will do, I will just consider the minimum distance of x and b. So I consider epsilon to be minimum of small x, let's say mod of x minus a and mod of x minus b. Okay, then what I will do, I will break it. So I will take it epsilon by 4 as small as I can. So I will break it and I will consider x minus epsilon minus by 4 comma x plus epsilon by 4. So that means this is one example, and I will take a minus epsilon by 4 comma b plus epsilon by 4. So means this one. Alright, so this is how one can define. And we know that in case of by unibodal theorem we can characterize the closed subsets in case of R with the closed interval. So it is enough to work with this closed interval. And finally another one, there is something called T4 spaces. So here basically any two disjoint closed subsets can be distinguished with disjoint neighborhoods. For example, you consider v1 comma v2, this is a subset of this, these are closed subsets, of course non-empty. Then there exists u1, the subset of x, and u2, the subset of x, this open set, and u1 this contains v1 and u2 is containing v2, but u1 intersection with u2, this is disjoint, this is empty. Alright, so this is called T4 space. Now see one thing, that we have several kind of definitions we have seen, like T1 space, T2 space, T3 space and T4 space. Remember that in case of T1 space, the properties of separation is there in case of T1 space, but the difference is that here is not the disjointness of the neighborhoods, it has been imposed here. Like in case of x1, let us consider that capital X is T1 space, is a T1 space. So let's take x1 comma x2, any two distinct points, right? So I can do this kind of thing, that x1 complement and x2 complement, these are open subsets. but x1 complements this contains small x2 and x2 complement contains small x1. Okay, so that means here is not any guarantee that small x1 complement intersection small x2 complement, these will be empty set. There is no guarantee for that. So the special case one can readily cook up is that if we consider x to be a two set elements like this and we impose discrete topology, then we can easily say that x1 complement intersection with x2 complement, this has to be empty set, right? So then in this case T1 space will imply T2 space. This is an example when T1 space is a T2 space. Alright. So now we have seen examples of T1 space and T2 space. The very important example for the students who are interested in algebra is the following, that a non-example of T2 space. So there is something called Zariski topology space. This is not T2 space. If you are familiar with this statement, then it's very good. But if anyone is not familiar with this statement or the Zariski topology, let me just briefly give overview that suppose that A is a ring, right? Of course, commutative ring with unity. Then we consider that the collection of all the prime ideals, which is known as spectrum of A, it's said to be spectrum. Basically, collection of all the prime ideals of A. Okay. Then we define a topology on this via the closed set. So we define the closed set of spec A like this. So it is V of I, where I is any ideal of A, and V of I is defined as set of all P belongs to spec A such that I is inside P. Alright. So you can easily check. So it's an exercise for you, that Vi is closed subset. So you know how to choose a define a closed subset. I mean prove a closed subset so that it is closed under finite union and closed under arbitrary intersection. And if that gives you a topology on the Zariski topological, I mean with this closed subset you can define a topology on this spectrum of A. So this spectrum of the ring with associated with the Zariski topology is a non-T2 space. So that means if you consider that any 2 points, let's say P1 and P2 belongs to spec A, let us consider that P1 is inside U1 and P2 is inside U2, where U1, let us see, it is of the form V of I1 complement and it is V of I2 complement. All right, so that means, and V of I1 complement intersection with V of I2 complement, this is empty. So that means what, if I take the V of E1, I1 union with V of I2, this has to be the entire spectrum of A. Okay, now P1 is in I1 complement, so that means I1 is not inside P1 and I2 is not inside P2. So that means what, P2 mass belongs to V of I1, okay, and P1 mass belongs to V of I2. So I1 has to be inside P2 and I2 has to be inside P1. Alright, now note that V of I1 union V of I2, this is nothing but V of I1 times I2. It is very easy to check. Like for example, suppose we consider that any prime area, let's say Q belongs to V of I1 union with V of I2. So that basically means that I1 is inside Q or I2 is inside Q. So for any of the cases, I1 times I2 being inside I1 intersection with I2 has to be inside Q. Okay, and conversely, suppose I1 times I2, this is inside Q. Okay, so that means what, let Q does not belongs to V of I1 and neither of in V of I2. So that means what, there exists certain small x1, this belongs to I1, and certain small x2 which is inside I2, but x1 and x2 both are not in Q, right? So that means what, x1 times x2 which must belongs to I1 times I2, but this does not belongs to Q. So here is the contradiction, right? So that means I1 plus V of I1 union V of I2 has to be inside, has to be same as V of I1 times I2. All right, so this is nothing but spec of A. Okay, so that means, so now here is a key point, that suppose we consider A to be Kx, where K is in algebraically closed field with uncountable cardinality. So for example, you can consider K to be as C itself. Okay, so it is Cx. So what is spec of A then? Spec of means it is spec of Cx. Okay, so spec of Cx means, so then as we have C is an algebraically closed field, so if we take any polynomial, that can be split into product of 1 degree polynomials, right? So like if we consider any Px belongs to Cx, we have defined this kind of decomposition. It is can be written as product of I equals 1 to n, it is Pix, where each Pix is of the form, let's say lambda Ix minus mu I, because we know that in case of algebraically closed field, any polynomial can be decomposed in linear factors. So these are the prime elements, right? So that means in case of spec Cx, it is nothing but it is a collection of all lambda Ix minus mu I, such that lambda I and mu I both belongs to C. Okay, so it means basically it is collection of all the 1 degree linear polynomial. All right, so if it is my spec of Cx And what is, now let us consider any v. I is any ideal of Cx is an ideal. Now note that C is a field, that means Noetherian. Noetherian ring, that means this entire Cx is also Noetherian ring. So Noetherian ring means this I, each ideal must be finitely generated. That means I is finitely generated. That means I can be written as product of, it is ideal generated by certain f1x and so on up to fnx. So what is my v of I? My v of I is basically union of v of fix. Okay. Now each v of fix, this has to be finite, because if we consider any fi is a polynomial, then what I will do, I will get the linear factor decomposition of fix, and v of fix is nothing but a collection of all those linear factors. Okay, so now it is finite, so I equals 1 to n, so it is finite union, and finite union of finite sets, so that means v of I, this has to be finite. You can check it, v of fix is finite. For example, like let's say fix has the following decomposition. Let's say, okay, let us take a1x times b1x, both are linear. Okay, so of course fix belongs to yeah, I mean, of course ideal generated by a1x, this contains fix. Okay, means ideal fix is inside a1x, it's a prime element, right, as well as inside b1x. Now suppose we consider that so basically a1x comma b1x both belongs to v of fix. Okay, so this is subset of this. Now if we consider any other polynomial, let's say q1x, okay, this contains fix, so that means a1x times b1x, this is inside q1x. Now remember that a1x is linear, b1x is linear, and q1x is also linear. So that means what, this has to be, I mean, q1x must be of the form, it is basically something like so it is something like lambda times a1x times b1x. Now if we you can make it now each are basically linear. Each, this is linear, this is linear, this is linear, and this is of course constant. So it is must that q1x has to be same as one of these a1x, so or q1x has to be same as b1x. So basically there is up to certain product of certain unit element is there. Okay, so at least one of them is there. So this is basically this v of fix is nothing but a1x comma product of up to say let's say anx, so where if we consider fix to be as product of, instead we have considered here two polynomials, product of two polynomials, but in general if it is the product of n number of linear polynomials, so this is the collection, this is V of fix. So this is how one can define. So V of fix, this is finite, and it is basically finite union, so V of I has to be finite. So now see here that if we consider V of I, now this is the main thing, that we have got that spec of Cx, this is infinite, but V of I1 and V of I2 both are finite. So that means union of two finite has to be finite. So this is not possible. So this is a counterexample. Okay, so that's a very beautiful counterexample that the algebraic students in algebra should be very interested, and this is really very important tool to work with some more result in commutative algebra and of course in algebraic geometry. So you have just given the definitions and the exercise that I will leave it. Can you find the relations between these? Means just try to show that whether T1 implies T2 or T2 implies T3 or T3 implies T4, this kind of things. Okay, like you assume that any space is T1 and try to show that whether it is T2, or if it is not, then where is it T3 or any kind of thing is there. So just one-to-one relation in between these two kind of spaces. Okay, so this is a very starting of the separation property. In the next session we will start with some more on Hausdorff spaces, the continuity properties of Hausdorff spaces and normal and irregular spaces. So I think you have, it's a very short lecture that we have just today started here with this topic. I think you will do a very rigorous verification with all these definitions and examples and non-examples. I will encourage you to cook up with more examples of T3 spaces which is not T4. If you find any relationships between them, then try to get some more examples and non-examples. Alright, so let's stop it here. We will continue with more motivation of mostly T2 spaces in later series. Right? Okay, thank you very much.